You know that phone in your pocket or the computer on your desk? Well, every single one of them is packed with tiny silicon chips. But deep inside these little marvels of engineering, there's an invisible atomic-level battle going on that can make them fail. Today, we're going to dive into a hidden vulnerability in our electronics, a plague that threatens the very connections that make everything work. So it really all boils down to this one huge problem. You've got this incredibly complex, microscopic city humming away on a silicon chip, but it's totally isolated. How do you actually build the roads to get power and information in and out? I mean, the scale here is it's wild to even think about. Well, for decades, the answer was actually pretty elegant and kind of beautiful. Tiny little wires made of pure gold. Using a process called wire bonding, engineers could create these microscopic bridges from the chip to the outside world. It's this super delicate, high-precision dance, and for a long time, it really seemed like the perfect solution. But here's the thing, as our tech got pushed into tougher environments with higher and higher temperatures, this seemingly perfect golden bridge, well, it started to crumble. Engineers started discovering that the connection wasn't nearly as stable as they thought. Turns out it was hiding a secret, a really fatal flaw that was causing devices to just mysteriously die. This problem was so distinct and so destructive that it earned a pretty sinister name in the world of microelectronics, the Purple Plague.
Okay, so how did we even get here?
Well, it all starts with the materials they picked. For the wire, engineers chose gold. It's a fantastic conductor, and, this is key, it doesn't rust or corrode. For the contact pads right there on the silicon chip, they used aluminum because it's cheap and sticks really well to the silicon. You look at this on paper and it seems like a perfect match, right? Yeah, but when you smush these two metals together and turn up the heat, something really weird happens. They don't just sit there next to each other, they actually react. They form a totally new substance, a gold-aluminum compound. And this new stuff, which often has this weird purple color, is incredibly brittle and weak. It's not a solid connection anymore. It's more like a fragile crystal that can just crack under pressure. And look, this wasn't some one-in-a-million fluke. It's a well-known, well-documented problem. For any device that gets hot, and let's be real, that's pretty much all of them these days, this purple plague was a huge threat to its reliability. But why it happens? Now that's where the story gets really cool. So this isn't just about chemistry. It's way deeper than that. This is a story of betrayal, happening at the atomic level, a scale you can't even imagine. Okay, to really get this, you gotta picture how metals are built. They aren't just messy piles of atoms. Nope. They are arranged in this beautiful, repeating 3D pattern called a crystal lattice. You know, like when you see a perfect pyramid of oranges at the grocery store? Super orderly, super stable. That's what's going on inside a metal. So here's where that perfect little pyramid just falls apart. When gold and aluminum touch, their atoms start to move around, kind of swapping places in each other's lattice. But, and this is the whole problem right here, they don't move at the same speed. The aluminum atoms race over into the gold way faster than the gold atoms move into the aluminum. So you end up with more stuff moving out than moving in, leaving behind these tiny empty pockets called Kirkendall voids. The connection is literally eating itself from the inside out, getting hollow, weak, and eventually it just snaps. And if you want a number to really show you how bad this is, check out the atomic packing factor. It's basically a measure of how dense and strong the material is. Pure gold and aluminum, they're at 0.74, super tightly packed, very strong. But that new purple plague stuff, it's just 0.25. That is a huge drop. It's like going from a solid brick to a piece of styrofoam. The last thing you want holding your electronics together. Okay, so we've got this atomic plague on our hands, right? A connection that's hollowing itself out. How in the world do you fight the laws of physics? Well, this is where the engineers get really clever. Solution number one, basically build a wall. Engineers came up with a surface finish called ENIG. Think of it like a defensive sandwich. They put down a layer of nickel, and that nickel acts like a barrier, a security guard that physically stops the gold and aluminum atoms from mixing. Then they add a super thin layer of gold on top, not for the connection, but just to keep the nickel from rusting. Problem solved. All right, another way to fix this, just change the players in the game. Look, gold is awesome, but it's also crazy expensive. So the industry started a massive shift over to copper wire. Copper is way cheaper, and it's actually a better performer electrically and thermally. But of course, there's always a catch. Copper's fatal flaw? It rusts like nobody's business. So what do engineers do? They innovate, right?
They iterate. To solve that corrosion problem, they came up with palladium-coated copper wire. They basically gave the copper wire a tiny protective jacket made of palladium, and boom, you get the great performance and low cost of copper, but with the toughness you need for a bond that's gonna last.
But the wildest solution, the real game changer, it doesn't just improve the wire. It just throws the whole idea of a wire right out the window. This is about completely rewriting the rules, using what we call additive manufacturing, or, you know it, 3D printing.
Check this out. Instead of fumbling with a physical wire, a machine comes in and literally 3D prints a connection. It uses this aerosol jet to spray a super precise line of conductive silver ink, connecting the chip's aluminum pad directly to its package. This is a total game changer, because you completely bypass the gold aluminum problem. You create a brand new, stable silver aluminum bond that doesn't have any of these voiding issues.
So, what's the upshot of all this incredible engineering? What does it mean for the stuff we use every single day? Well, the impact is pretty amazing.
Okay, this chart says it all. They put these connections through hell, 250 degrees Celsius. The original gold aluminum bonds, our purple plague victims, they start failing pretty fast. But the 3D printed silver connections, a perfect record. 100% reliability after more than 1,000 hours. I mean, that's just an unbelievable improvement.
And that brings us to the big takeaway here. The reason your phone, your laptop, whatever, the reason it doesn't just fizzle out and die after a year isn't some accident. It is the result of decades of brilliant materials science and clever engineering, of people fighting these invisible atomic-level battles so that our stuff just works.
And that really leaves you wondering, doesn't it? As we keep pushing technology, making chips smaller, faster, hotter than ever before, we're shoving materials into places they've never been. The battle against the purple plague might be over, but you gotta ask, what other weird atomic-level plagues are hiding out there, just waiting for us to find them?